Last class, we talked about numerical solution of Laplace's equation, and we worked through a few examples of the numerical solution of the Laplace's equation. We were using a method that's called the relaxation method, which is a well-established method for partial differential equations. This class, we're going to look at the diffusion equation, another sort of classic partial differential equation. We're going to look at a couple of examples of the diffusion equation and solving it numerically. They're drawn from thermodynamics rather than electrodynamics, and they're using the leapfrog method, you'll see what that is, rather than the relaxation method. And this reflects the fact that for solving partial differential equations, it's kind of piecewise approach to different methods for different equations to suit your particular problems. Okay, so just a few words of introduction about the diffusion equation. It's also the heat equation, and our examples of the diffusion equation are going to be drawn from the world of heat and heat flow. So just a few words of introduction on that. So as I hope we all know, heat flows from hot to cold. We can, in simple terms, if we have two objects, one hot and one cold, calculate the final temperature of the combined hot and cold object when the heat is flowed from the hot one to the cold one. That's a famous problem of thermodynamics. A question related to that, that's a more difficult question, is how fast does the heat flow from the hot one to the cold one? How long does it take the two objects, the hot and cold, to equilibrate at a common temperature? So that's the type of problem we're working on today. So we're going to be using the diffusion equation. We'll be solving the diffusion equation, or the heat equation, solving the heat equation. And it's going to tell us how fast or slow heat flows from a hot object to a cold object, that question. So heat flows by various mechanisms. In vacuum, heat flows only by radiation. In a gas, heat flows predominantly by convection, like in the atmosphere, it's by convection, dominantly by convection. Or in the oceans, convection, important part of heat flow. And then in solids, heat flow is predominantly by conduction. It's by the collisions of electrons in the solid with other electrons in the solid, higher energy electrons, where it's hotter, colliding with cooler, lower energy electrons, where it's cooler, transferring energy from the region that's higher temperature to the region of lower temperature. So that's conduction. In a metal, tend to have high thermal conductivities because there's lots of conduction of electrons, and they're the mechanism of transferring, dominant mechanism of transferring the energy from the hot region to the cold region. In insulators, on the other hand, they're not only electrical insulators, they're thermal insulators. There's less free electrons to transfer energy from one region, the hot region, to the cold region. So we're going to be working on conduction as a heat transfer described by a heat equation or diffusion equation. The diffusion equation or heat equation is a partial differential equation involving space and time. So it involves differentials with respect to space and time. And actually, it's second order in the differential with respect to space, first order in the differential with respect to time. And here is that equation. So it's a second order differential with respect to space is in proportion to the time differential, first order time differential, time, and there's a coefficient of proportionality in the context of a diffusion equation. It's called the diffusion constant. In the context of the heat equation, this might be called the thermal constant or the thermal diffusion constant. Anyway, that's the equation that we're going to be solving. This is the equation that reflects, dictates the flow of heat through a solid, and it's the equation that can tell us how fast or slow something will heat up or cool down. One little point. This, we'll be calling this thermal diffusivity today. Maybe more common term is thermal conductivity. They're not the same thing. The thermal diffusivity and the thermal conductivity are not the same thing. They're related things. This is a relationship between the thermal diffusivity and thermal conductivity and the density of the material and the specific heat of the material. We don't need to use that today, but I just wanted to remark on that. Okay. Turns out that this differential equation describing diffusion, say diffusion of heat, or it could be just diffusion of particles. We've worked with this before in another context. When we were doing the random walk of particles, they diffused away from their origin, from their starting location, and there also, that's diffusion. So we're now seeing two ways that we can describe the same physical effect. The random walk way of treating individual particles and how they randomly walk away from some starting point or origin is kind of a microscopic version of the diffusion equation, where we think of a sort of large ensemble or a continuum limit of the number of particles or the little packets of energy, and that flowing away from a starting location. So the random walk work that we did with individual particles and the diffusion work that we're going to be doing with either heat or concentrations of particles are really just different ways, macroscopic, microscopic, looking at the same thing. And in that context, it's interesting just to think about specifically how the two are related. So in the random walk case, first bullet here, the random walk is characterized by kind of a step size in space of the particles, how big they step, and a time interval, time duration, how frequently they step. So kind of delta x and delta t characterize the random walk of particles, individual particles. That's the language of the random walk of the individual particles, specifying a delta x and a delta t. In the diffusion equation, well, the diffusion equation, as we said, is this relationship between the time and the spatial evolution of the number of particles, the diffusion of particles. It's a relationship specified by second order and first order differentials with respect to space and time. And it has a constant in it, the diffusivity constant, diffusion constant, d here. And that's kind of the language that describes how fast or slow the collection of particles will diffuse. So in one case, the random walk, you've got a language of the delta x's and delta t's of how fast the particles diffuse away from a location. In the other case of the diffusion equation, you've got a language of a diffusion constant that's characterizing how fast or slow the particles walk away from a certain location, how fast the ensemble walks away from that location. Those two things are therefore related to one another because they're just microscopic, macroscopic pictures of the same sort of thing. And you can figure out the relationship between the two by just considering we worked when we talked about the random walk, we figured out the root mean square of the random walking distribution of particles. You can do the same thing for the root mean square, the random walk of diffusion. So this continuum limit of lots of particles. The random walk in case of individually walking particles was just the root mean square was the number of steps you took multiplied by the square of the size of individual steps. So that's how the particles diffuse when you think about them individually. When you think of them through the diffusion equation, the result of the diffusion equation is that the root mean square of the diffusing particles is equal to 2 times the diffusion constant and the length of time that we've been watching the diffusion for. So we could equate these two equations and find the relationship between the diffusion constant, this quantity that describes macroscopically how the particles diffuse from a location, see how it's related to the individual steps in space and time that the particles are taking. And if you do that, then you find that the diffusion constant is just equal to the square of the spatial step size divided by the twice the time step size. So supposing you had particles who were undergoing a random walk, and they were say each nanosecond, each 10 to the minus 9 of a second, they stepped in their random walk a nanometer. So those are sort of atomic level scales. Their steps, their random walk is one nanosecond intervals and one nanometer steps. Then the diffusion constant corresponding to a collection of those particles undergoing a random walk would be the 1 nanometer squared divided by the twice the one nanosecond. So we've got 10 to the minus 9 nanometers squared, so it's 10 to the minus 18 meters squared, divided by 2 times 10 to the 9 seconds. So it's about 10 to the minus 9 is the diffusion constant in meters squared per second. So that's a way of seeing how the diffusion constant is related to the individual steps of the particles that are diffusing, or in thermal physics, right, the energy that's diffusing around. So when you measure a diffusion constant, you measure a diffusion constant, then it's a reflection of the little random walk that the particles are going and how big they step in how much time. Okay. So this is like just to get a better idea of how the diffusion equation works. To get an idea of how the diffusion equation works, especially in the context of the numerical solution of the diffusion equation, I'm going to imagine the diffusion equation is a function of space and time. I'm going to imagine that our space in this example of a diffusion equation, which is a one-dimensional space. So it's just one-dimensional space plus time. So the diffusion equation itself is just have 2 dimensions, space and time. I'm going to discretize space. So horizontally here is my space from left to right. I'm going to think about, rather than, we're going to go to thermal physics and think about the flow of energy around the diffusion of energy, where temperature is kind of a proxy for the diffusion of energy. But on this slide, I'm going to think about particles and the diffusion of particles. The rho 1 is the particle density at location number 1. And the rho 2 is the particle density at location number 2. And so on and so forth up there. Rho n is the particle density at location with the index k. So with discretized space, we've got a discretized picture of the density of particles in all these little buckets of discrete space, and we unleash them, and they're going to start diffusing around. Let's think about the time rate of change of the density of particles in this little element here. So I pick out one element, the ith element, that has one density, rho I, and that's going to change with time because of diffusion. What ways can it change in time? The number of particles in that little element, or the particle density in that little element? Well, these little arrows are meant to indicate different ways that the density or the contents of that spatial bucket or spatial bin can change in time, right? Particles could leave and go into the neighboring cell. So that's this little arrow that goes towards the left here, on the left-hand side. Particles could leave that cell and go to the neighboring bucket or cell on the right-hand side. That's the right pointing arrow on the right-hand side. So those are two possibilities. The particles could flow out of that cell. Then there's two more possibilities. The particles from the cell on its left, we'll call that I-1, some of those could flow in, and the particles from the cell on the right, we'll call that I+1, some of those could also flow in. So that's flow from the left into the center, flow from the right into the center. It's these two bottom arrow figures. So that's listing all the possibilities for the flow of particles into and out of that individual cell, in that ith cell in some particular clock. The rate of change of the number of particles or the density of particles per clock tick, or per unit of time, will be proportional then to the diffusion from the cell on the left is in proportion to its density, particle density, or its concentration, or the number of particles. So it'll be in proportion to that. That's particles entering. The contribution of particles moving from the right-hand cell to the center cell, that will be proportional to the density or the concentration of the particles in the right-hand cell. That's this little guy here. So those would cause an increase of the number of particles in the center cell. So it would be a positive contribution here. And then the other contributions are the leakage of particles or concentration from the central cell. So that's in proportion to its content. So there's a minus rho I here if they're going to the left-hand side, minus rho I here if they're going to the right-hand side. So those are the four arrows that we represented on the picture, the four ways that we can lose or gain particles or concentration that we represented on the picture. Here's just writing how they would contribute to the time rate of change of the density in this particular cell. So this combination of the density or the concentration in these three cells, to rewrite it like this. This is the combination of the contents of these three cells that measures curvature. It reflects curvature. That would be if there was no curvature in the distribution between these three cells, then this would be zero, because the central cell density would be simply the average of the two neighboring cells. But if there is a curvature, maybe there's a peak around rho I of the particle distribution, and that's a curvature, then this will be non-zero. And if there's a peak there, the curvature is going from positive on the left to negative on the right. It will be a negative curvature. If there was a valley here at this central cell, then the number of particles density was lower here than the neighboring cells, so that's a valley. There will be a curvature there too, because we're rolling down the valley from the left and rolling up on the right. That would be a positive curvature. Okay. This guy here does reflect the curvature, and the curvature is nothing other than the slope of the slope. It's the second order differential with respect to the position coordinate. So we could represent it like this sort of thing. So we've just visualized and derived the diffusion equation. We saw how the time rate of change of the contents of this cell is related to the spatial change in the across the neighboring cells. First order differential with respect to time is in proportion to the second order differential with respect to space. So the slope with respect to time of the contents in a particular cell is determined by the curvature with respect to space across the neighboring cell. The thing that we didn't talk about here was the diffusion constant. This is how quickly this happens or slowly this happens. So there's a diffusion constant in here between these two space and time derivatives. This is just a picture down here of these two cases that I mentioned. If you have a peak of the number of particles, the concentration of particles in the central cell, and a distribution like this hill, then the diffusion equation says, well, look, you've got a negative curvature across those three cells. So you're going to have a negative rate of change of the number of particles in this central cell here. Let's just say that more particles will leak out of the central cell than move in from the neighboring left and right cells. If you have a distribution like this, a valley across those three cells, and so there's a lower number of particles in the central cell, that's a positive curvature as a function of spatial coordinate. So positive curvature as a function of spatial coordinate means that the rate of change of the contents of the central bin is going to be increasing. The slope is positive, which is again what you would expect. If you have less counts in the central cell than in the neighbors, the more of the neighboring particles are going to come in from the left and right than are moving out from the central cell. So that's how the diffusion equation works. We talked about it as if it is particles when we talk about the heat equation. The same equation, it's just that we're kind of talking about energy, packets of energy moving in and out. We typically in the heat equation use not energy or heat, we use temperature. We're using temperature as a proxy for heat or energy. So the temperature also obeys this diffusion equation. Okay. This was just a picture I made of, sketch I made of diffusion based on the random walk material that we did sometime earlier on in this class. So we would start a particle randomly walking in space, and we would follow how it diffused away from the origin. Here I just imagined this one-dimensional problem of particles diffusing in space. I ran with 5,000 particles starting at the origin and plotted the position of all the individual particles or the distribution of the particles as a function of the number of steps in their random walk. So they started at the center here, and then I'm plotting them in orange, green, and red. And orange, green, and red. There's more colors. As they walk away from the, over time, as they randomly walk away from the origin. So this looks exactly like diffusion of the particles from an original position. And we can actually calculate the diffusion constant in this case. Now we understand that this is represented by a diffusion equation with a diffusion constant. So the diffusion constant would be, we saw that it was equal to the size of the individual steps. so the size of the dx, divided by twice the time interval of the individual steps. So if in the units of dx and the units of delta t, units of delta x and delta t, you work in those units, then the diffusion constant is 1 half. This typo should be 1 half. That's the diffusion constant in the kind of natural units, step size of the diffusing particles and the step interval, time interval of the diffusing particles. And as I say, if they were diffusing 1 nanometer every 1 nanosecond, that's a diffusion constant that is 0.5 times 10 to the minus 9 meters squared per second. Okay, let's get on to a real problem. I'm going to work through my code shortly on solving the diffusion equations. I'm going to work through a problem of diffusion of heat through a window pane. We're going to imagine that it's colder outside and it's warmer inside, like it is right now. And we're going to watch heat flow diffuse through the window and watch temperature as a function of time. This is the problem from the homework, the assignment. So this is the problem that you solve. This is a similar sort of problem. In this case, you've got a big bath of cold water in blue here. You've got a hot steel rod that's dropped in the cold water. The rod is actually, to keep this problem a one-dimensional problem rather than a high-dimensional problem. So we're going to imagine that this rod is perfectly insulated around its cylindrical walls, the cylindrical body, so that there's an insulator, cylindrical insulator, but it's in contact on the left-hand end and the right-hand end, the cold water bath. So this is also a problem of you would solve, and you're going to solve numerically with the diffusion equation and with the leapfrog method. You drop this insulated, partially insulated steel bar that's hot into the cold water. Heat's obviously going to flow in from the left-hand side and the right-hand side, not from the side walls, and that rod is going to warm up, cool down to the temperature of the water, and you're going to watch how that rod cools down to the temperature of water over time. You'll be solving the heat equation of the diffusion equation for the rod. I put this one in here because this is one of the cases, one of the few cases you can solve it analytically. So this is actually the analytical solution.
So we're supposed to make a 2D grid for this. Should we just leave a little space on each side of the rod? I'm just interested in why we need a 2-dimensional grid for that.
Yeah, you're going to need a 2-dimensional grid for that. For the same reason, I'm going to go to the pane of glass example.
Okay.
We also need a 2-dimensional grid for that. But the reason we need a 2-dimensional grid for the pane of glass is not because of pane of glass where we think it's 2 dimensions. Okay. The dimension that we're interested in is the thickness. And the other dimension is time. Okay. In this case, this is what are the dimensions that are important? There's one dimension in space that's important, the length of the rod, and then the other dimension is time. So both today's, it's a very good question, both today's window pane problem, which kind of looks like a limit of a 2-dimensional object, is one-dimensional in the problem because we're thinking about the thickness of time. And then it resembles this one, which looks one-dimensional for the rod, but it's one-dimensional plus time again, so it is 2-dimensional. Okay, this is the solution that you should get. As you know intuitively what's going to happen. You drop the 100-degree Celsius steel rod into the cold water, if it's insulated on its cylindrical sides and only in contact thermally at the two ends, then the heat's going to flow out of the warm rod through the two ends. The heat's going to flow out, and so a moment after you've dropped it in, say 1 second after we've dropped it in, 1 second after you've dropped it in, heat is starting to flow out. It's flowing out, energy is flowing out, but really only the far left of the rod and the far right of the rod knows it's in contact with something that's cold. And the flow of heat, the flow of energy is, and the change in temperature is at the far left and far right hand ends of the rod. If you're living in the middle of the rod, right, you don't know that you're going to get cold soon, because just the influence of the cold bath hasn't reached you yet. But as time elapses, right, after 10 seconds with the orange curve, still in the center, you don't know that the ends of the rods are in this cold environment. But this cold environment is heading towards you. It's heading towards you from the left and from the right as heat is flowing out to the left and to the right. If we wait long enough, we see the rod cool like up to 500 seconds and the red curve here. Now the rod is all getting cold. It's not 0 degrees Celsius yet, not the temperature of the bath, but it's getting near that equilibrium. 500,000 seconds. We're almost there, almost at 0 degrees Celsius along the length of the rod. So diffusion equation allows us to calculate this sort of time scale for this happening. This is happening over hundreds of seconds. You know, if you just know about specific heats, then maybe you can calculate the final temperature of something if you put a hot thing and a cold thing in contact. But you with specific heats alone, you can't calculate how long it took for the hot thing to get cold or the cold thing to get hot. Here we can do that. Okay. Yeah, this is the problem that I'm going to solve. So it's exactly like a pane of window here, with cold outside and hot inside. The pane of glass is thin, thickness is small compared to its surface area. So here's my picture of this problem, in which upstairs here, this is inside our classroom, and outside is the air. It's not cold today. Outside is the colder temperature. So we've got 24 degrees inside and 0 degrees outside. And then the unrealistic part of this problem is that somehow the window just happened to be at 10 degrees Celsius, so some temperature in between. And obviously, it's going to equilibrate so that the face of it that's in contact with the warm air will reach the temperature of the warm air. The face of it that's in contact with the cold air will reach the temperature of the cold air. There'll be a temperature gradient across the window from 24 to 0 degrees Celsius, and of course continually heat is pouring out of the room into the outside, from inside to outside. This is the result of my calculation. Because we know what was going to happen, right? We start off with the window at 10 degrees Celsius from the inside of the room to the outside of the room. So the inside of the room, the window is cooler than the room. The outside of the room, the window is warmer than the outside. So we start here, and then again, heat from the warm room will start to flow in. You see that happening here, even after a fraction of a second. And heat from the outside part of the window is starting to flow out, even after a fraction of a second. And as time evolves, we see the heat flowing more and more in, warming up the the left-hand side of the window and heat flowing out over here and cooling down more and more of the right-hand side of the window until we get a constant gradient from the inside to the outside. And that's corresponding to the kind of steady state in which heat is just pouring out of the room constantly through the window. Yeah.
Are these problems assuming that the air or the bath is big enough that they don't get warmed up by the?
Yeah. Just to make it a reasonable problem. The bath that we threw the rod in was big, and so it didn't warm up. And the atmosphere outside is big, it's not gonna cool down. And the room, well, it's big-ish, but we've also got the heating on, so it's not gonna cool down. So, yeah. Okay. So we've got 3 slides about how we numerically solve this problem. We numerically solve the diffusion or heat equation. And we talked about it a little bit already. We're going to obviously discretize, as we always do, the independent variables in our particular problem. And we said, whether it's the window pane or whether it's the steel rod, these are actually 2-dimensional problems. One of the dimensions is the relevant spatial coordinate, the thickness of the window, or the length of the rod, and then the other dimension is the time. We have a dimension of time in the diffusion equation. And we're going to discretize both of those. And so this is a picture of that. Time is running horizontally on this picture. And the position coordinate is running vertically on this picture. So this is a space-time picture of the window pane. It's a space-time picture of the window pane that we need because we've got space and time as the independent variable. So we're looking for a solution that is a function of space and time. So we need a space-time picture of the discretized coordinates. So the inside of the window, where it's warm, is then represented by this horizontal line up there here in red. So that's at the position coordinate, corresponds to the inside of the room, and we're just watching it over time. And then the blue line at the bottom, that corresponds to the outside location of the window. And again, we're just watching it over time. So walking to the right from the left is just evolving with time. Walking through the window pane from the inside to the outside is walking from the top of this block to the bottom of this block. So that's the direction in which we walk through the window. Okay, so if you remember, the diffusion equation has differentials with respect to space and time, has a first order differential with respect to time, and a second order differential with respect to space. We've got to turn the diffusion equation into a difference equation in space and time coordinates. And we've got recipes for turning differentials into difference equations, and we're just going to apply those recipes. Here I started with the space part. So the space part of the diffusion equation is a second order differential with respect to the spatial coordinate. Second order differentials with respect to the spatial coordinate, they pick out the curvature of the function, so the slope of the function, and the curvature of a function in the as a difference equation can be written like this by considering in your difference equation for your discretized space, can be written like this involving the function at 3 separate locations. With 3 separate locations, you can sample enough to find the curvature find an estimate of the curvature. It's like sampling enough with the Taylor expansion to get an estimate of the curvature. And this is the expression for the curvature. So we're going to equate this with the second order differential with respect to time. So look, it's sampling the function, the temperature, at position x, at position x plus a, and at position x minus a. So those are the 3 points that we're looking at the temperature gradient of. With those 3 points, we're figuring out whether there's a curvature or not to the temperature. We saw that if the temperature at the center point was simply the average of the temperatures of the 2 other points, then that corresponds to no curvature, what this equation said. But if the temperature at the center is not midway between the 2 other temperatures, then that temperature of this that will correspond to a curvature. It could be positive, it could be negative curvature. Anyway, this is one thing we've got to stick in. And this is the other half. We've got to discretize time coordinate as well. We've got to change our differential equation for the with respect to time to a difference equation in terms of time. And we know we've met how to do that too. This first order differential of the function with respect to time just determines the slope of the function. We can finally write down the slope of the function as a difference equation. Again, this comes out of Taylor expansion. We just need to sample the function at 2 different times. H is the t plus h and t. So these are the 2 times. H here, like A on the previous slide, is just a little increment in time rather than an increment in space. And so this is the replacement we're going to make here. So we've got, all goes back to the earliest, slightly nostalgic, earliest class on Taylor expansion, how you can write the first order differential, the second order differential of a function in terms of the function's values at nearby or neighboring points. We're just using that. We're just applying first order, second order Taylor expansion. Now I've got to take these 2 equations, this one and that last one. So this last one, remember, we discretized space and the spatial lattice spacing is A. This one, for the time, we discretized time, and the discretized time interval is called H. And we're going to plug those into the second order partial differential equation. That's the diffusion or heat equation. And that's what I've done here. So I've plugged those 2 things in and just rearranged it a little bit. I rearranged it a little bit so that the value of the function at the later time appears in the first order difference equation for the corresponding to the time differential is related to the values of the function at the earlier time and at different positions. So if you want to picture that, I've sketched it over here on my space-time grid. This is the value, this is the function at the future time at a particular location. It's determined by the values of the function, the temperature of the current time at that location, and also at the neighboring locations. And this is what this equation is saying. The value of the temperature at the future time is equal to the value of the temperature at the current time, plus something that's going to change it, which comes about literally through diffusion. So it involves the diffusion constant here. And it can come about from changes in the heat or energy temperature in these 3 points. The center point more than the 2 neighboring points. And so this is our difference equation that we're now going to solve. Okay. The procedure that we're going to use for solving it when we implement it on the computer is not a relaxation procedure. It's not called the relaxation method. It's called a leapfrog procedure, leapfrog method. In this case, we're calculating a future temperature from a current temperature. We do that. We do it all the way along the rod or through the glass. And then when we've got the future temperature, we're going to do the next thing again. We're going to take that as the current temperature, calculate the future temperature all the way along the rod. And then we'll do that again and again. Take the current temperature, calculate the future temperature, and work our way forward in time. So we're kind of leapfrogging in time. Right? We go from current time step to the next one. Do all my work. Then I go from this, which is now a current time step, to the next one. Do all the work I've got to do. So we're leapfrogging our way forward in time. In the relaxation method, we really just, firstly, we just swept over the two-dimensional space in the lattice equation, in the Laplace's equation. We swept over, in our problem, we swept over a two-dimensional space in the XY grid. And we could have gone, we went from, like the top left corner down to the bottom right corner, but we could have picked any direction to go. This problem really has a kind of flow to it, a direction to it. It's why we're using this leapfrog method. So it's different from the two-dimensional grid in the Laplace's equation, where we could have walked over the grid in any direction we chose. This is a two-dimensional grid, but the direction that we're going to walk is forward in time, leapfrogging forward in time. Oh yeah, put here just some comparisons between the leapfrog method, which we were just introducing, and the relaxation method, that was last class's introduction. Here are the two equations for implementing them. I just derived, or we just derived this one. T prime is the T prime is the future temperature, and T is the current temperature here. And the index i's are the spatial coordinates in this equation. Upstairs here, this was the fact that the potential at any location in a space grid is the average of the neighboring potentials. And in this equation here, the grid is represented by the i's and j's. So the i's and j's are just the indices that walkers over the grid. So in the upper one, I'm not really distinguishing much about the i's and j's. They're just two variables and two spatial coordinates. In the lower one, I'm really distinguishing between time and space in this equation. They're treated very differently. So that's why partly why one is a relaxation method, where we can walk any way we like over the grid. The other one is a leapfrog method, where we have to walk a certain way through the space-time grid. Another difference is this has a parameter in it. Has multiple parameters in it. The multiple parameters are, one is a diffusion constant, so some characteristic of some material that we're working with, the parameter in there. Also, we're walking in two different dimensions. We're walking in space and time, and so that there's parameters describing the spatial and time lattice in here. So all these constants go into this correction here. This right-hand part is a correction by which the temperature changes. So the change in temperature, the difference between Ti and T prime I, is determined by this object here, which is multiplied by the diffusion constant and the spatial and the time discretizing of our continuous space-time. Just want to check I went through everything here. I think I've discussed everything here. Maybe the one thing I didn't discuss in bullets here is that in the relaxation method, we sweep through the grid in X and Y, update the values of the potential. Then we swept through the grid again in X and Y and updated the potential again. And then we swept through again and again and again. We might have swept through thousands of times the space-time grid. That's very different from the leapfrog method. In the leapfrog method, we're sweeping through the space-time grid only once in a very prescribed way. So we just sweep through that space-time grid. Remember my plot of it, from the left-hand side at early times towards the right-hand side at right time. And each step we kind of walk vertically up and down in space to calculate all the temperature of all the spatial locations. So we're not iterating in the leapfrog method. We were iterating in the relaxation method. Okay. Here's the code. I'm just running in now because it might take a little bit of time to run. Okay. It's not a very long code. It's just this one cell here. And most of it's either setting up initial values of parameters or plotting the results for the temperature as a function of time. The actual calculation is just a few lines. So let's just walk through this. Again, of course, I'm importing NumPy because I'm working with arrays. I'm importing matplotlib because I'm going to plot my results. I import math also because there's one little function that turned out to be useful for me when I did the plotting. So the import of math is not a necessary thing. The import of math was just how I did a feature of the plotting. So let's start walking through these cells. Well, we need to know something about the glass, something about the glass window. We need to know the thickness of the glass window. And I've set that to be 5 millimeters. We don't need to know the cross section of the glass window. We just need to know that it's much, the other dimensions are much larger than the thickness of the window. So it's just looks like a sheet of glass. Thin thickness, small thickness compared to the dimensions of the cross-sectional area. The other thing we need to know about the glass is its thermal diffusivity. So this is a number, a constant in the diffusion equation, that sets the scale of diffusion. If that number is large, right, a diffusion, that would be a conductor, and you'd get heat would flow readily. If that number is small, that would be an insulator, and the heat would flow more slowly. So we need to specify the thermal diffusivity of glass. And so I had looked that up, I think. I have put in this number here. That's in meters squared per second. That's the units of the diffusivity. And again, it's a reflection of what's going on microscopically. The little random walk of the electrons, of the hollow electrons, and towards the cold region. So it reflects those little microscopic random walks of the electrons. And we said that if the random walks happen to have spatial steps of 1 nanometer, and they happen to have time intervals of 1 nanosecond, then you get a diffusivity that would be about 10 to the minus 9 meters squared per second. So I just took kind of randomly atomic size or microscopic size dimensions in space and time, and I figured, you know, that diffusivity is about 10 to the minus 9 meters squared per second. Our glass diffusivity is several hundred times that, but you know, it does give you a scale that, you know, the random walks of the mobile electrons in the glass, or whatever's carrying around the heat in the glass, are sort of scales of, maybe they're scales of 10 nanometer steps every nanosecond or something like that. So it does give you a little internal picture of what's going on in the glass at a microscopic level. Anyway, we know the thickness of the window. We looked up the diffusivity. We need to discretize space and time. So I happen to pick the thickness of the glass. I'm going to divide into 100. I thought that's sufficient resolution, sufficiently fine resolution for the spatial coordinate. And the discretization of time, I happen to take little steps of 1 millisecond. I thought the heat's not going to flow faster than that sort of time scale. So I picked 1 millisecond. So these are just sort of intuitive things, right? If you've got 5 millimeter thickness, you probably don't want to pick 1 centimeter size for your lattice in space. If you've got heat going through a glass, you probably don't want to pick an hour for your time interval, or your discretization of time. So this sort of reasonably sensible numbers. The discretization of space, the discretization of time, and the diffusivity all roll into one coefficient in the difference equation that determines whether the temperature is going to change. The scale of the heat. So calculating is here, so I don't have to keep writing h times b divided by a squared. Okay, we need to specify our initial conditions. Yes.
What was that for equation for the approximate time?
Oh yeah. When I run it, I'll show you that. But there's a rule of thumb. There's a useful rule of thumb. We're gonna calculate how long it takes for the glass to thermalize, reciprocate. Like you'll calculate how long it takes for the steel rod to pull down. You'll come up with a sort of time. You'll come up with the evolution as a function of time. But there's a rule of thumb actually for, it's more than a rule of thumb. It's sort of derived from the diffusion equation. You can calculate a time constant for the warming up or the cooling down. And that time constant, and now it's approximate, it's a rule of thumb because, you know, it's a time constant that depends on the dimension, spatial dimensions in your problem. Well, look, I've got a window and maybe my spatial dimension is obvious there, it's the thickness of the window. I've got a rod, the spatial dimension there is the length of the rod. But supposing I got a hunk of iron ore and I drop it in, well, what is the relevant spatial dimension there? It's a bit more complicated. Anyway, the rule of thumb is the time constant is determined by, I can't see that. The time constant for heating up, cooling down, based on solving the diffusion equation, is order of the relevant spatial dimension scale squared divided by pi squared times the diffusion constant. Now, if you think about it, well, where did that come from? Firstly, it does make sense, right? If the rod were longer, then it's going to take longer time for the heat to, thermalize it. If the window pane were thicker, it would take a longer time. So we expect it to depend on L. If the diffusivity was larger, it would flow more readily, then the time taken would be smaller. If the diffusivity was smaller number, insulator, then it would take longer. So we'd expect the diffusivity in the denominator, and we expected the length in the numerator. Now, that's not an expectation about what powers they appear in the numerator and denominator, but we also know that the time constant is a time, and we're making it out of these two parameters that are important in the problem. One of them has a length of, one of them has a dimension of meters. And the other one has a dimension of meters squared of a second. So the only way to make a time out of this is to have length squared divided by diffusion constant. Because then you've got meter squared divided by meter squared per second, and we get a time. So I think you can sort of wave the hands and understand all the contributions. They make physical sense, and the units make sense. Of course, I'm not explaining the pi squared. That comes out of the diffusion equation. Yeah, that's why you solve the diffusion equation. And we'll see what this number is, and we can compare it to our calculation. It's just a sort of benchmark. Okay, we were going down to the initial conditions, weren't we? Which is here. So this is the outside temperature, T low. T high is the inside temperature, and T middle is the initial temperature of the glass that somehow I magically arranged. So we define those as those variables here. Look, we're going to do this leapfrogging. We need an array of the current temperatures along the length of the rod, and an array for the future temperature along the length of the rod to do the leapfrogging. So I've got to initialize these arrays. So I create these arrays with a number of elements that corresponds to my spatial discretization. I set up the initial condition for the window. Remember, it's on the inside, it's at the high temperature. On the outside, it's at the low temperature. And everywhere in between, from one step away from the warm inside to one step into the window away from the cold outside. So this slice here is at the middle temperature to start with. So this is just the starting point of the glass is hot, warm, and then cold. The cold temperature on the outside of the pane, the warm temperature, cold temperature on the outside of the pane, and warm temperature on the inside of the pane, they're not going to change. We already know that for the future time what they are. So I'm assigning the future, these variables for the future time here. I don't have, well, so I want to plot the results. The way that I plotted the results, and I can't remember why I plotted the results this way, really. But I plotted the temperature of the rod at different moments in time, different instances of time. So I made one-dimensional plot, so the temperature at a certain time, then a later time, then a later time. I didn't do it like the way I did it in the last class, which now strikes me as would have been a smart thing, which is make a two-dimensional plot, so a heat map of the with two axes corresponding to temperature and position, and the color in the map corresponding to the temperature. That would be a very reasonable, straightforward thing to do. I think I made it more complicated for some reason, and I'm just going to plot a number of one-dimensional plot of the temperature along the rod at different times. I'm going to plot the temperature of the rod at 1 millisecond, 10 milliseconds, 100 milliseconds, 1 second, and 10 seconds. This guy here, I don't think I've ever talked about, we talked about lists, we talked about arrays. In Python, another structure is dictionaries. So dictionaries are useful. Maybe this is why I wanted to say. Dictionaries are kind of useful. Dictionaries are arrays of elements that have two components to them. They have a key. Every element in a dictionary has a key and has a value. So you have a key and a value, and here there, when you define it, it's separated by this colon. So here's the key in green, here's the value, it's a string in red, key and string, key and string. I'm just defining my times to be the keys in my dictionary, and the values to be some labels that I can put on the graph. So this defines the dictionary. This little calculation here, you can grab the keys from the dictionary. I found the maximum value of the keys, it's the 10 seconds here. This is going to, I'm going to stop calculating the time evolution after 10 seconds. This is just finding the maximum time that I'm going to plot. I'm just going to plot out to that maximum time. Okay, so see how I do that later on. I use a while loop, and I'm just going to keep stepping in time. Remember, we're leapfrogging until we reach the end of the windows that I want to plot for. And as I walk out through time, I'm going to keep track of the time here. So this is the variable. This is my proxy for continuous time. It's my discrete time that I'm going to keep incrementing by my time increments. Okay, so here's the entire calculation comes down to these two lines here, basically. Well, no, it comes down to this loop and these lines here. The loop is the leapfrogging, right? Each time I go around the while loop, I've taken a step forward in time. Doing this every time I go around the while loop, calculating future temperature distribution from the current temperature distribution. How do I calculate the future temperature from the current temperature? T prime from T at each location labeled with I. I do it with that one equation that we developed, that difference equation. And C, remember, is this combination of the spatial and time increments and the diffusion constant. So it comes down to this one little equation here. This is the piece that's multiplied by C and changes causes the temperature to change. And it depends on, for a given location on the window position in the window pane, it depends on that location's current temperature and on the neighbor's current temperature. So each time we go through this for loop, we kind of leapfrog. We've updated the temperature profile for the new moment in time. So this is the leapfrog. After we've done that, I got this little line here where I just, I'm going to replace the current temperature with the new temperature that I just calculated. So that's the key bit here. I just make that replacement and I increment time. This is where I do the plotting. So I defined, I think it was 6 times that I want to make one-dimensional plots for the results at. And this is where I call the plot function to plot those temperature distributions. Look at the plot function. I'm plotting the temperature distribution. And I'm going to label it with plot time, which are the values in my plot times dictionary. So this is how I plot each temperature and label it correctly with the time. Now we're going leapfrogging hundreds, thousands, millions of times, right? I don't want to be making hundreds, thousands, millions of plots. I only call this if the time, the current time in my leapfrogging matches the plot time that I stored in my dictionary. So this loop here is iterating over the plot times that are in the dictionary. And I'm checking if my current time is equal to a plot time. If it is, I'm going to make the plot. Now, because of we're very, very early on in the class, we talked about floating point precision and, the limitations of floating point arithmetic. To get this to work, because it didn't work, I actually had to use this function in math. So this is why I imported math. Because of the limited number of digits in my floating point numbers, and time that was equal to a plot time was not being evaluated as equal to the plot time because some, digit, the last digit was not agreed. So I found this math function that is close, which allows you to set how close two numbers have to be, two floating point numbers have to be, for you to consider them to be the same. So this returns true when the time and the plot time are within some tolerance. And this got me around the problem of the floating point array. Anyway, it's a long. I spent more time talking about the plotting on this than I talked about the algorithm, because the plotting was more work than the algorithm. The algorithm is just highlighted in blue. In blue in this while statement. Okay, here's the results. Temperature vertically, position horizontally in units of my spatial increments here, but in units of temperature in Celsius vertically. Blue, the moment we installed the window and it's hot on the inside and cold on the outside, and it was 10 degrees Celsius through the body of the window. So blue is where we start from, or maybe it's a millisecond after we just started. A little bit of heat energy is flowed in on the left, a little bit of heat energy is flowed out on the right. We wait 10 milliseconds. 10 milliseconds and we got the orange color. Most of the window doesn't know that it's been stored in a location where it's warm inside and cold outside, but just at the edges, it's starting to become aware. Green hot, 4 times. This is now a 10th of a second. Red hot, now a second. The heat is flowing in on the left, the heat is flowing out on the right. After 10, 100 seconds, 10 and 100 seconds, we've almost got steady state. We've got a constant temperature gradient from the hot inside to the cold outside. And so that's what we've done with our leapfrog method. Let me just go back to your question about that. This is that rule of thumb for how long does it take to reach equilibrium is the L squared, 5 millimeters squared, over pi squared times the diffusion constant. I don't remember what the number for that was with graphs, but came up with 7.5 seconds.